Okay, for this video, I'll be going through electromagnetism for pure physics. Okay, success criteria A. Draw the pattern of the magnetic field due to currents in straight wires and in solenoids, and state the effect on the magnetic field of changing the magnitude and or direction of the current. Okay, we have learned in the previous chapter in magnetism that when a current flows, okay, it will produce a magnetic field around it. So this relationship is for this chapter, it is called electromagnetism. Okay, so what happens when current flows in a straight wire? The previous chapter we did mainly on solenoid. Okay, so if current were to flow through, right, then you must use your right hand grip rule to determine what is the pole on the both ends of this solenoid. Okay, but for this chapter we will focus mainly on straight wire. So again, when current flows through, okay, whether in a straight wire or solenoid, it will produce a magnetic field around it. Okay, so it actually forms concentric circles. Okay, so this concentric circle is not like your wave fronts. Okay, in the other chapters, in waves, we covered wave fronts, right? So for wave fronts, if they have the same wavelength, that means the same depth, then they will have equal distance. But for the magnetic field produced by this current, it actually produces concentric, right? And we have learned that the further away it is to the previous circle, that means the field strength is getting weaker. Okay, so this is what is meant by concentric circle. So for wavefront, usually, or if the question states that it is of a constant depth of water or things like that, then they will have uniform wavelength. So the gaps between the circles are the same. Okay, so this is an experiment done. Okay, so let me explain the figure. So this is the north, the magnetic north of Earth. Okay, and we see that there is a cell that later, when the switch is closed, there will be current flowing out. So this is the positive, that means the current will be flowing this way. Okay, when the switch is closed. But when the switch is open, both compass will point to the north. Okay, the geographic north. Okay, so this is what is being mentioned here. When no current flows through XY, this part of the wire, there's no current because it's open switch. The compass needle both point to the north. Now, compass B is actually below the wire. That means if I have the wire, okay, the compass is actually below it. But compass A is actually above the wire. So this is compass A, it is lying above the wire. But the thing is, both of them are pointing in the same direction, which is the north of Earth, right? However, when the switch is closed, okay, current will flow. Okay, so this is the direction of current. So we find that both wires are now not pointing in the same direction. In fact, they are pointing to opposite direction. So why is this so? We'll explain later. Also, we can look at another setup. Okay, so when no current is flowing in the conductor, so this is the conductor, okay, and no current is flowing, okay, all the four compasses at each corner, they are all pointing in the same direction, north to south. So I would say that this is the north. Okay, but when a large current flows through, it will produce a magnetic field, right? So this is the direction of the current. Okay, and we find that the compass needles are now affected by the magnetic field of the current, and they are all pointing in different direction. And we see that if they are actually pointing in a circular manner. Okay, so when the card was lowered or raised, the direction of the needles do not change. Right, this suggests that the magnetic field produced by a conductor forms circle around the conductor. When the compass on the card are repositioned further away, the needles again form circle. So this suggests that the magnetic field forms concentric circle around the conductor. The direction doesn't change, okay? But of course, with one set of 4 compasses, we are not able to see the strength of the magnetic field. Okay. However, when the direction of the current is reversed, the needles deflect in the opposite direction. So if you compare this diagram, okay, where the current is going to the top versus this diagram where the current is going downwards, okay, the direction of the compass changes. So is there a way to determine? Yes, we can use the right hand grip rule, okay, but take note, right hand grip rule, right now we are going to apply to straight wire. For right hand grip rule that we learned in the previous chapter for solenoid, okay, let me just do a very quick recap. Okay, so this is the thumb. For solenoid right hand grip rule, the thumb points to the north, okay, whereas the fingers are pointing in the direction of the current. Okay, so maybe we can do a very quick exercise to see if you can recall. So we have this. Okay, let's say current goes this way and comes down this way. It is very important for you to trace the direction of the current on this part of the wire, okay, because this part of the wire, the direction of the current will tell us how to position our right hand so that our fingers represent the direction of the current. So if I were to do that, then it is exactly like what is shown here. Therefore, it will be a north here, it will be a south here, okay. But now we are going to apply right hand grip rule on a straight wire. So for right hand grip rule straight wire, it actually looks like this. Okay, so again, this is my right hand, okay, but now this points in the direction of the current, okay, it points in the direction of current, and therefore this direction will be direction of magnetic field. So there's no north and south, because actually in a circular magnetic field, right, there is an infinite number of north and south. So if I were to say here is north, then here will be south, then south, north. Okay, so yeah, so this is right hand grip rule for straight wire. It is used to predict the direction of the magnetic field around a wire that carries a current, and this rule states that if the thumb is pointing in the direction of the current, which is different from your right hand grip rule for solenoid, the curved fingers will be pointing in the direction of the magnetic field. Okay, so we can apply this, okay, but before that, I will need to talk to you about dot and cross, okay, dot and cross, right? So before we apply this, we must know the direction of the current. So let's say now we are looking at the wire from the top. All we can see, right, it is a circle, okay, because we are putting our eyes here, okay, all we can see is a circle, okay. But if we are looking at the lengthwise of the wire, we would see a long length, right? So it is very different. So let's say now I were to ask you to look at the wires on top, you will actually see a circle, and if you were to view it from the bottom of this straight wire, it will also be a circle. Okay, so how do we represent the direction of the current? We use dot to show out of page or coming towards you. Okay, and we use cross to show into page, going away from you. Okay, so you can think of it as like an arrow. Okay, the arrow actually has a pointed end, right? And at the back there's also a shaft, right, the feathers. So if I were to look at the arrow and the arrow is flying towards me, all I can see is a dot. Okay, but if I'm the person who is shooting the arrow and I am viewing at the back of the arrow, okay, I would see that the shaft or the feathers of the arrow actually makes a cross. So this cross means that the arrow is away from a viewer. Okay, and if it's a dot, that means it's coming towards the viewer. Okay, so please remember this. So for this question, for this example, the current is actually going from bottom to the top, and I'm looking at the top part. So it will mean that the current is coming towards me. Okay, so now we apply the right hand grip rule, whereby the thumb represents the direction of the current. So if you are looking at my screen now, you should have your thumb pointing to yourself. You should have your thumb pointing to yourself, because I gather that you're viewing this video from a vertical screen. Right? So if you are viewing it from a vertical screen, your thumb should be pointing to yourself. What does the thumb represent? The thumb represents the direction of the current, and it is a dot. That means the current is going towards you, right? So your thumb should be pointing to yourself. And then because you're using a right hand, you'll see that the fingers are curling towards you. So how does it look like? I'll try to draw it. So these are your fingers. Okay. And this is your thumb, something like that. Okay, you'll see that the thumb is pointing towards you, whereas the fingers are curling in a anti-clockwise direction. Okay, how about now we reverse the direction of the current while still looking at the top part. Okay, now the current is actually going from top to bottom, but because we are looking from the top, right, all we see is a circle. And because the current is going away from me, because it's going downwards, we would use a cross. Okay, and again, how do we represent the direction of the current? We used our right hand grip rule, right, where the thumb represents the direction of the current. So if you are again viewing it on my screen, on your screen, okay, your thumb should be pointing towards your screen. Your thumb should be pointing towards your screen, and you'll find that your fingers are curling in a clockwise direction. Okay, I should not try to draw because it looks very ugly, my drawing. Okay, so how do you know that you're applying this rule correctly? So I say again, if you are viewing at your screen when you're watching this video, your thumb, which represents the direction of the current, should be pointing towards the screen. And then your right hand, the finger should be curling in a clockwise direction. Okay, so you see that actually the circles, they don't have the same gaps in between, right? The closer the field lines are together, the stronger the magnetic field. So as I get further and further away, okay, the gaps between the magnetic fields will be larger and larger, which means that over here the magnetic field is the weakest. Okay, so try to do this and see if you get the correct direction. Okay, then what happens if the currents are different magnitude, where you see I2 is stronger than I1? Okay, we see that we'll have more field lines drawn to show that we have stronger magnetic fields. You see that the lines, we have more dense lines. Okay. Okay, so the strength of the magnetic field of a current carrying wire increases when the current is increased, right? So how about current flowing in a solenoid? So we already learned right hand grip rule. Okay, so how do we increase the strength? Okay, it can be increased by increasing the current, increasing the number of turns per unit length. Okay, do not say increase the number of turns. Okay, this is incorrect. Okay, or by placing a soft iron core, because soft iron core is easy to magnetize and demagnetize, right? Therefore, the purpose is to concentrate magnetic fields. Okay, because it allows magnetic field lines to flow through it, it will sort of concentrate the magnetic field lines through it. Okay, so that's for success criteria A. Now, success criteria B, describe the application of the magnetic effect of a current in electromagnets, which is your circuit breaker. So your circuit breaker actually uses electromagnet. However, this wasn't really explained when we are doing practical electricity. Now we'll take a look. Okay, so under normal conditions, when the switch is turned on, current will flow through the solenoid. So when current flows, it will actually produce a magnetic field. Okay, so this is a very important concept in electromagnetism. It will produce a magnetic field. Now, when the current is below the limit, that means it's within the working range, the magnetic field of the solenoid is weak, and therefore it does not attract the iron bolt. Let's take a look at this. Okay, so this is the current flowing, right? And because current flows from high potential to low potential, so the current will flow through the solenoid. Okay, so let's just take a look and recap what is the where's the north and the south. So if the current were to flow this way, okay, can't really see, you need to trace the direction of the current here. Okay, so if you were to apply right hand grip rule for solenoid, north will be here, south will be here. Okay, maybe you can practice and try. Okay, so there is a magnetic field that's being produced by the current flowing through the solenoid, but because the current is below the limit, the magnetic field of the solenoid is weak and therefore does not attract this iron bolt, which is a soft magnetic material. So the solenoid and iron bolt are not in contact, therefore the current flows normally. Okay, so this is under normal conditions. And now there is a surge in current when there is an electrical fault. Okay, so the current increases. So if the surge exceeds the limit, the solenoid becomes an electromagnet that is strong enough, or you can say it becomes stronger. So the key point here is that it must be stronger because you are comparing. Before that, there was already a magnetic field produced, but now because of the increase in current, it will be now stronger, and if it's stronger, then it will attract the iron bolt. As a result, the plastic plunger is free to move, you see. So, and because there's a spring action, right, so this will cause the contact to be turned off. Okay, so this is an example of an electromagnet. Now, the concepts are all the same for this circuit breaker. Okay, the concepts are all the same, just that sometimes the designs will be different. So what are the important things that you need to say? So it's only when there's an electrical fault, then the magnetic field produced by the solenoid is stronger. Okay, so therefore it will cause an attraction and it will create an open circuit. Okay, so after the fault has been traced, the circuit breaker is switched on again by depressing the reset switch, which is this one, the reset button. So then it will push back and then the contact will be complete and then the current can flow again. So let's take a look at another design. Okay, so again, current flows. So this is our solenoid, right? So why is it that it does not attract this iron latch? It's because even though current is flowing, it's within the working range. So the magnetic field that is produced by the solenoid is weak. Okay, so therefore it will not cause the safety bar with the spring to spring out. So there is still contact. So therefore the current flows normally. Okay, and again, when there's an electrical fault, right, there's a surge in current, so the magnetic field produced by the solenoid is stronger. Please add in this, is stronger, so that it can now attract the soft iron latch. So you have to make a comparison. Okay, That is success criteria A and B.